And the holomorphic QFT.
Great, thank you so much for the invitation. It's been a lot of fun getting to chat with you all before. I gave a little bit of a crash course on some of the things, but I'll try to keep it accessible to those that weren't able to make it earlier. I just wanted to mention that this story I'll be telling you is based off of a couple of my recent works with Brian Williams and with Surya Raghavendran. One from, I guess, August, and then two from last Friday. This first one is a sort of purely mathematical paper where we developed this notion of a raviolo vertex algebra. This is where this ravioli will be coming in. And then these are two, I guess this is an application of ravioli business. And this one is something that fed into both of these works and is related to symmetry enhancements in these types of holomorphic topological quantum field theories. But the sort of first thing I say, I hope isn't too controversial, but it's that symmetry is sort of behind everything, almost everything we can do in quantum field theory and string theory. The sort of prototypical example of where we get really, really robust constraints from symmetries is in a two-dimensional holomorphic or chiral quantum field theory, where we have current algebras and Virasoro algebras that constrain the forms of operator products and the spectrum of my operators and their correlation functions. And this is a remarkably powerful realm of the world to be in, and it's one of the places where we know the most about quantum field theory. My aim is to advertise the fact that this should be a more general phenomenon than just two dimensions. This holomorphic topological story I'll tell you about is quantum field theory in 3 dimensions, where we have not quite as much, but still a great deal of control as in this two-dimensional holomorphic setting. And so it turns out that these ravioli vertex algebras have many parallels with vertex algebras in the usual sense, and I hope to highlight some of those as we go forward. So to start, I wanted to remind you a little bit of where the utility of holomorphicity comes from in two-dimensional holomorphic or chiral quantum field theory. So really the two things that we use in holomorphic and chiral quantum field theory are the notions of, well, holomorphicity and also, I guess, locality. So holomorphicity give us lots of symmetry. For every local operator O, this is going to depend on just its sort of holomorphic position on my Riemann surface, can lead to an infinite tower of symmetry operators, topological defects in my theory. And this comes from holomorphicity. You remember that if I look at contour integrals of holomorphic functions, they only depend on the contour up to homotopy. And that's a signal that there's some topological aspects of the corresponding symmetry operators. For every operator O, I can consider a contour integral over some curve gamma, dz z to the n of my operator O. And this is going to be a topological defect of my quantum field theory, essentially because of the Cauchy theorem. I can move this contour around in my correlation functions. As long as I don't hit any local operators along the way, it's the exact same thing, which is, of course, what we consider to be a symmetry or a topological operator. So what this does for us is, if we take our gamma to be a circle centered at some point W. I'm just going to take W to be 0 for simplicity. So we take a small circle centered at the point 0. This operator O gives me an infinite number of linear operators acting on the space of local operators. So for every operator I'm going to call O1 and every integer n, I'll just use the notation O1 comma n. I can send any other local operator O2 at 0, that's where this 0 is, to the contour integral I've written here. So this is integral over this small circle centered at 0, dz, z to the n, O1 of z, O2 of 0. Of course, this infinite tower of linear operators on the space of local operators is just encoding what we know to be the operator product expansion. So that usually takes the following form. The operator product of O1 and O2 can be written as a formal sum of local operators at 0 with some dependence on z. So these linear operators, O1 comma n, arise in the operator product expansion as the linear operators acting on O2, thought of as a local operator at 0, in this formal sum. So in this way, the operator product expansion that you know and love from holomorphic quantum field theory is just a really concise way of encoding all of these topological symmetries in one compact expression. Of course, the relation between these two, maybe I guess I should put a factor of 2 pi I. The relation between these two formulas is just the usual Cauchy formula. So in this way, holomorphicity and locality, giving us all these symmetries, is encoded in these operator product expansions. And another way to phrase all of this is that these linear operators depend on a local operator as well as n. N showed up in this sort of integration kernel here. So the clever way to say it, the symmetries O1n, well, this n are labeled by holomorphic functions on C star. So z to the power n for n an integer. These are just the usual holomorphic functions on C star. But a better way to say it might be to instead say it's a holomorphic function on a configuration space of 2 points on the complex plane, modulo overall translations. So my quantum field theory is translation invariant. Didn't really matter that I put my operator at 0. I could put it at any point W. And these linear operators, these O1n's, are labeled by holomorphic functions on this configuration space of points on my spacetime. But of course, we can do yet better. Holomorphic functions are better replaced by Dolbeau cohomology of the same space. Turns out all of these spaces are affine, so you can just look at holomorphic functions and you get everything. But as we'll see, life isn't always that easy, and you really should consider all of the cohomology. Yeah.
When you say the symmetry of O1, then are labeled like algebraic functions.
Yeah. So what I really mean is this n is a an integer, and rather than thinking of it as an integer, you should really think of it as a holomorphic function on C star. This kernel you put into the integrations. And so you could just say, okay, for every local operator and every integer, I have these symmetries. But the more refined way of saying is that for every holomorphic function, I could have put any holomorphic function here and gotten a symmetry, sort of like O1 comma F. F is my function. And this is just some particular choice of basis on that space of functions. And rather than talking about just global functions, it turns out we can just get away with that here. But you should really think Dolbeault cohomology of this configuration space, not just H0. Okay, so this is the old stuff. Now I'd like to tell you about one dimension higher. So we're going to work in a three-dimensional quantum field theory that's part holomorphic and part topological. You're probably more familiar with the 2D holomorphic quantum field theories, especially if you've played around in string theory or in boundary vertex algebras or anything like that. These 3D holomorphic topological quantum field theories might be a little bit more exotic. They show up in some of Mina's earlier work. But the most common setting that I see them in is in twisted quantum field theory. So as we'll see later, many of my favorite examples come about from taking a supersymmetric theory in 3 dimensions, performing a supersymmetric twist that isn't fully topological, but only topological a little bit. So the context we're going to be in is a quantum field theory. We're just going to talk about local operators and things like that. I'll mention some global aspects later. But we're going to consider 3D quantum field theories on a space-time of the form C times R, where I have holomorphic coordinates Z and Z bar on the complex plane and a smooth coordinate T on the real line. And for my quantum field theory to be holomorphic topological, that R, rather than write holomorphic topological forever, I'm just going to call it HT. Have correlation functions independent of the Z bar I and Ti, the anti-holomorphic and real coordinates of the insertion points of these local operators. So this is correlation functions of local operators. Globally, there's a notion of a transverse holomorphic foliation. So rather than just working on flat space, you can work on curved manifolds equipped with a transverse holomorphic foliation, where locally everything looks like C times R, and the coordinate function, or sorry, the transition functions are holomorphic in these 2 coordinates, and they take a particular form in this T coordinate. It's not super important because I'm mostly going to be working on this flat space, but globally, we have functions, we have a transverse holomorphic foliation. And explicitly, let's see what I want to say. This is locally a foliation sort of generated by del t and del z bar. There's a way of saying it in terms of sub-bundles of the complexified tangent bundle, but that's not quite so important. The statement is that there's a sheaf of such functions, a sheaf f, that I'm going to call h sub ft. And these are all functions on my space-time such that del z bar, or maybe I'll write it, Lie derivative in the z bar vector field, Lie derivative in this holomorphic one. So in terms of that involutive sub-bundle of the complexified tangent bundle, you just say for every vector field in that certain sub-bundle, this Lie derivative kills my functions. These are just functions that depend on z and not z bar and t in this sort of flat space limit. So correlation functions are going to depend on the z coordinates of my insertion points, not z bar or t, are elements, or I guess functions. Maybe I should say holomorphic topological functions on the configuration space of n, which this is like the number of insertion points of C times R. So one thing to mention about this is that operator product expansions, we can imagine taking the coincident limits of these correlation functions. So I bring my points close together. These are going to be encoded in the operator product expansions of my local operators, are non-singular. As in, things only depend on z. There's no z inverses or z minus w inverses or anything like that. Did you have a question? Okay. And there's a pictorial way of seeing this. I can imagine having a local operator at a point zt and another local operator at a point ws. And because my correlation functions only depend on z and w, not on t and s, I can take the coincident limit where I keep their t separation, the separation in the real line, finite, but I send their z separation to 0. So I can consider a configuration w and because correlation functions only depend on z and w, they can't depend on t and s, and because this is a local quantum field theory, singularities can only arise when they're literally the same point. So correlation functions depend on z minus w, but they can't be singular when we send z to w because we can keep their separation finite while keeping this difference or sending this difference to 0. And if you're familiar with higher dimensional complex analysis, this is an analog of Hartog's lemma, which says that any singularity is removable and dimensions higher than 1. So this is a 3D holomorphic topological analog of Hartog's lemma. Every holomorphic topological function on C times R minus a point. This is like 2-point correlation functions, if you will, where one of my operators is at 0. Extend to a holomorphic topological function on C times R. And of course, on C times R, holomorphic functions are just, well, holomorphic functions on C. Sorry, holomorphic topological functions are holomorphic functions on C. But as we saw before, we shouldn't just look at functions, we should look at derived functions, or the cohomology of the appropriate structure sheaf. In our setting, the structure sheaf is just going to be this sheaf of HT functions. So this brings us to the namesake of this talk, the raviolo. So all correlation functions are non-singular, but there is interesting cohomology in this ring. In particular, there's more information in correlation functions than just looking at these simple things we were doing before. This cohomology, I remind you, is the analog of holomorphic functions. And so at the end of the day, what we'll find is a tower of symmetries analogous to the ones that we saw in the two-dimensional setting, labeled by these cohomology classes. So let me tell you what that is. So in degree 0, this is just the holomorphic functions we talked about before. They're just holomorphic functions of my coordinate z on C. And then in degree 1, it turns out that there's also an infinite number, and a slick way of writing it is polynomials and derivatives of a certain degree 1 cohomology class I'll call omega. And there's a way to write it in terms of differential forms as follows. T dz bar minus 2z bar dt divided by this root distance cubed. So as before, we had positive powers in z, that's the analog of h0. The negative powers of z can all be reached by applying derivatives to the function 1 over z. And if you remember your complex analysis, 1 over z is actually a Green's function for del bar. Turns out that this one form here is also a Green's function for the differential defining these holomorphic topological functions. So this is a Green's function for the differential operator. Oh, it's not showing up. Oh, sorry. Thank you. Is that a little bit better? Okay, this is a Green's function for I'll write it this way, but it's a little bit of a lie. And if you'd like me to explain the correct statement, I'm happy to. But morally, it's the sum of the Dolbeault differential on C and the de Rham differential on T. So in the same way, we have a propagator showing up and derivatives of the propagator. These will be the analogs of sort of the singular terms in our operator product expansions. Yeah, I'll spell out the analogy once we sort of have everything in front of us. So there's a relation in this cohomology. There's nothing in higher degree. We just have H0 and H1. So we have two types of relations. One of them is sort of trivial based off of the statement I just told you. Omega squared is 0. There's nothing in higher cohomological degree, so 1 plus 1 is 2, and so omega squared is 0. But there's also a relation that says z omega is 0. So this ring has 0 divisors, which is kind of annoying, but that's just the way she goes. And so because derivatives and multiplication by z don't commute with one another, you get some interesting higher order relations. And a convenient way to collect them all is to define a one form omega n, which is just some -1 to the n over n factorial nth derivative z omega. And the relation can be succinctly written as z to the n times omega to the m is equal to omega to the m minus n for n less than or equal to m, and 0 otherwise. And you should think of this as being the analog z to the n, z inverse to the m equals 1, or sorry, z to the m plus n, n minus m. So we have 0 divisors in this ring, but that's just how it works out. There's no way around it. But we do have an analog of the Cauchy formula I was telling you before. So rather than integrating over a S1, we're now going to integrate over a 2-sphere. We have the same sort of first part. Rather than 2 pi I, we end up finding an 8 pi I. Omega to the n is delta n0. So this is the same sort of formula as you saw in complex analysis. Yeah, definitely. And so this will roughly be the type of ring we're going to be playing with, rather than holomorphic functions with the usual residue pairing from the Cauchy type of formula. We now have this ring of holomorphic functions on C, so polynomials in Z, together with these degree 1 generators omega n. And there's a Cauchy integral formula in this 3-dimensional setting. So this is one form on C times R minus a point. And this S2 is the linking sphere of that point we removed.
This is the 2-dimensional
dz times omega is a 2 form. Yeah, great question. Thank you.
And also maybe a question about this omega. You say it's a Green's function for this operator. So how should I think about that? Why this little omega? Why the heck this particular? Are we going to use the explicit form for this little omega, or is this?
No, the thing I was trying to get at here was that there's many different perspectives on what this cohomology can be realized as. There's this sort of holomorphic topological differential forms on C times R, but it's also going to be sheaf cohomology of the structure sheaf of the raviolo. And that's the next thing I was going to say. Okay, so thank you for setting me up. There's a couple other descriptions in terms of tangential Cauchy-Riemann cohomology, but I don't want to say anything about that. There's an equivalent algebraic. In some sense, this was a smooth discussion so far. There's an equivalent algebraic description.
You mentioned the word Cauchy-Riemann, so it's like reminds me of this something like boundary or something complex, pseudo-complex.
So what I meant was you can think of S2 as a submanifold in here, and the sheaf of HT functions induces some structure on S2. It's not a complex structure. It's a tangential Cauchy-Riemann structure. Yeah.
You have a boundary of some domain, and it's like
yeah.
And you have this normal foliation.
Yeah.
Where's the R?
Yeah, definitely. So the equivalent algebraic description is in terms of this space, the raviolo. So rather than working with smooth things, you can work totally algebraically. This space goes by many names. One of them is the plane with the doubled origin. That maybe is the one that you're more familiar with. And it's sort of algebraic incarnation or infinitesimal algebraic incarnation. It can be realized as a disk or maybe a formal disk glued to another formal disk. I'll call this W, over a shared formal punctured disk, and the transition function is not quite the one that you use for the projective plane. It's this sort of non-Hausdorff space where you glue away from the origin. And so the statement is that this holomorphic topological cohomology we were talking about before on C times R is isomorphic to the just sheaf cohomology of the structure sheaf of the raviolo. So you can forget everything I said before about smooth things and work in this raviolo setting. So you can work totally with algebra. And the sort of picture you should have in mind is this S2 we're using before isn't super well suited to the transverse holomorphic foliation of space-time. It sort of intersects this is like the T direction, and the sort of complex planes are sort of along the height of our sphere. So it's not quite it's not particularly well suited to this transverse holomorphic foliation. And so instead, what you should do is consider our favorite Gaussian pillbox, which is just two disks with a cylinder attaching them. And this point that we removed in the center of our sphere is just in the middle of our Gaussian pillbox. But of course, our theory is topological in this real line. So we're free to squeeze this thing as we will. And so we end up with a space that looks like I've taken two disks, this top one and this bottom one. This is like dz and this is dw. And I glue them together, but I need to remember the fact that I removed this point in the middle. So I glue them away from the origin, which is where this sort of non-Hausdorff gluing comes about. So this raviolo is the space that we're going to be trying to understand, it will be the space whose holomorphic functions or derived holomorphic functions control the symmetries of one of these holomorphic topological quantum field theories. So I was saying earlier that operator product expansions only see sort of H0 in this space. How do we get at a higher cohomology? And this is why I couldn't stop talking about descent earlier. We're going to be able to access those things via a notion of descent. Descent is something that goes back way to Donaldson theory and the topological setting. Natalie Paquette and I wrote a nice review of aspects of descent. And if you aren't familiar with it, I highly recommend those notes. I've been told they're excellent. So rather than thinking of a theory that's genuinely holomorphic topological, we're going to work with a slightly weakened version of that. So we're going to assume our theory is weakly holomorphic topological. And this is really the context of supersymmetric twists and so on. What weakly means is I've got some differential Q, something like a BRST supercharge, if that's the language that you've learned. And in addition, I have two additional fermionic nilpotent symmetries, QZ bar and QT. This is like the BRST charge. And if you like these words, these are homotopies for translations. And it's not just all translations, it's Z bar and T translations. And the important relations that they satisfy encapsulate this homotopy property. So the bracket of Q Z bar is momentum in the Z bar direction, and similarly for the T direction. And the real utility of this is that it's the thing that makes trivial translations in the anti-holomorphic and smooth coordinates Q exact. So more precisely, if I have some local operator O, its Z bar derivative, which is up to factors of I that I'm not going to worry about, the bracket of O with this PZ, and then we can write this as follows. And this is assuming if O is annihilated by this BRST charge, it's a Q closed local operator, then this thing is itself Q exact. If O isn't Q closed, then you have a similar formula where there's another term that you can get by throwing a Jacobi identity at the first one together with this bracket I've written here. And similarly for del TO, this is equal to 0 in Q cohomology. And this uses QT acting on O. So from this, we can do this descent game we were talking about earlier. We define a new one-form valued local operator using these. So for any local operator O, I can make this one-form valued local operator O bracket 1. And it satisfies this descent equation. If I act with my twisting supercharge Q on this one-form operator O1, this is equal to del bar C plus D R O if O is Q closed. And if O isn't Q closed, then there's another term that you saw earlier, but I won't write it here. And so now what we're going to do is we're going to use these descent operators, these one forms, to define, in the same way as before, some integrated operators that can be used to define symmetries. So for any operator O1, and for every integer n, I hope this looks familiar, I'll define a new local operator. Oh, sorry. I can act on a local operator O2 at the point 0 and get a new local operator, which is going to be an integral dz over 8 pi I, z to the n, O1 of z, O2 of 0. And here I take one descendant. So this is a 1 form. With that extra factor of dz, I get a 2 form. And I can integrate it over this 2 sphere that we've been talking about before. So this should look exactly like what we had before, but now we have a descendant here. And we're integrating over a 2 sphere. If you've seen descent before, this is by no means a new thing. O and Yagi found these a long time ago, where they organized these brackets into a lambda type bracket. Here I've just sort of taken the Fourier modes of those lambda brackets they found. And the punchline is if O1 and O2 are Q closed, then so too is this bracket. And I'll stress that this is a local operator at 0. So this is a way of taking local operators and getting linear operators on the space of local operators, exactly as we did before. No. So this n should be thought of as like the H0 of our structure sheaf. So we saw up there, or maybe erased earlier, I'll stress it again here, n is bigger than or equal to 0. We don't have negative powers of n. In some sense, these are like the holomorphic functions on C that we put in here. And yet better, what we can do is define another type of operation, sort of analogous to the thing that we did before, but I didn't quite write it. Where for any cohomology class,
sorry, just a stupid question. I thought you said that OP is a holomorphic, but you want n to be positive.
Yes, yeah, it's only positive n's. The negative powers of z, quote unquote, will show up in a higher cohomological degree. So here, more clever thing to do is to allow the entire structure sheaf to show up, or a cohomology of the structure sheaf, not just H0. These were just H0. These higher things here can be anything in H0 or H1. So for every element of this sheaf cohomology, we get a linear operator on operators, and these negative powers of z, or at least the analog of them, are when we take omega as omega. So what I mean by that is dz over 8 pi I omega n O1 Oh, I forgot to mention the bullet notation. This bullet is O1 plus its first descendant. There's also a second descendant that I haven't mentioned. So when omega is a 0 form, I just reproduce this formula up here. But when I take one of my 1 forms, like this omega up there, this is another infinite tower in addition to these. And using that Cauchy formula I wrote before, this is just going to reproduce the usual operator product of derivatives of my fields. In the same way that when I plug in negative powers of z in the usual OPE formulas, I reproduce normal ordered products of derivatives of my fields. Okay, so I'm definitely running out of time, so let me just get to the operator product expansion. When did we start? 10 after? Okay. Okay, then I hope what is coming next will be clear. We have these 2 infinite towers of symmetry operators. Half of them correspond to the genuine operator product expansions we were talking about before. The other half correspond to these descent brackets. And here we only have n greater than or equal to 0. If you'd like, you can make this minus n minus 1. That's n. Sorry, no, this is minus n minus 1. And then this is n negative. So we see n positive reproduces the descent brackets, and negative reproduces normal ordered products in the same way that we had before. And so what we're going to do is we're going to organize this into an operator product expansion. But it's not an operator product expansion in the usual sense. It's a sort of homotopically enhanced version of an operator product expansion. So I have my 2 local operators, O1 at some point zt, O2 at some point 0. Oh yeah, yes. Z comma t. And then it should also be here. Maybe up there, and maybe, yeah. Sorry, thank you for that. So we're just gonna do the same thing we had before. We'll have 2 types of terms. So for n, let's call it greater than 0, greater than or equal to 0. We'll have omega n, bracket O1, O2, n 0, plus some n less than 0, z to the minus n minus 1, 1 over n factorial, derivative to the n minus n minus 1, O1, 0, O2, 0. And so this is exactly the form that we had before, where this term before is what we were calling O1 minus n minus 1, O2. Ooh. I think it's that one actually. And this is also O1n, O2 at 0. Where here n is negative and here n is positive, but it's the exact same formula that I had before, modulo replacing z inverse goes to omega 0, or more generally, z minus n minus 1 is identified with this 1 form omega n. And this is for n bigger than or equal to 0. Z to the n is just z to the n. So what we have, just to reiterate, this term right here encodes the usual operator product expansion that we talked about before. This is the thing that's not got any poles whatsoever. This is the genuine physical operator product expansion. This term here is a little bit more. It encodes these higher terms in the OPE, these descent brackets, and it actually has an interpretation as operator product expansions of O2 with O1 and its descendants. So together, this is an OPE of O1 and all of its descendants with O2. And this first term corresponds to the zero form part of this story, where I have O1 and O2. This term here corresponds to O11 and O2. And those formulas I had up there, where I was able to realize these linear operators as residues in some suitable sense, just follows from this Cauchy formula that I have since erased. And this, this formula together with that Cauchy formula I wrote before is equivalent to those linear operators we had. In the same way as holomorphic quantum field theory, we could do Cauchy integrals of operator product expansions to peel off these local operators.
So you're trying to define the OPE of O1 and O2? I say it in those.
So this expression, let me, oh no, I can't use, this expression here, I guess maybe I don't want to include that term. This expression here is a generalization of the genuine operator product expansion. The genuine operator product expansion just includes this term right here. These operator product expansions are non-singular, and that's encoded in the fact that I only have like positive powers of z showing up in this line here. But there's more information available to you when you take into account the weak aspect of the holomorphic topological theory. Namely, when you talk about a weak theory, you have these higher operations, secondary products, if you will, that encode more information than just the operator product expansion. They include these descent brackets that we talked about before.
So it's the usual naive one, which is have given up with like a
Just this term, yeah. Yeah. Exactly. And so that's why we're taking an operator product with not just the zero form O1, but also the one form O1 bracket 1. So this expression, this operator product expansion, is an operator product expansion in the proper sense, where I don't just consider the local operators, but also their descendants. Yeah.
So we're integrating the first two, we're taking the first descendant. Does it give us any additional information about integrating the rest of the descendants?
So this is a 3D TQFT, so that would be an integral over all of space-time. And those don't lead to higher operations, but actually deformations of your theory. So you can add to your action an integral of the second descendant dz, and that'll, if you take like a chiral operator, corresponds to turning on like a superpotential. So those top form descendants give you deformations. These sort of n-1 dimensional things give you sort of actions of local operators on local operators. Yeah.
So just a conceptual question, like, so the principle of extending OPEs by including descendants is something you can do pretty much any theory when it makes sense.
Mm-hmm.
So are you saying here that basically like to generalize the OPE from 2D, like I want to be able to besides just like, oh, that's singularity and you need to take into account the H1 of structure of raviolo.
Yeah. Yeah, definitely. I think that's exactly how you should think about it. In the purely topological setting, you could play this exact same game, and you have sort of the bracket coming from the cohomology of like an EN algebra showing up here, together with that like collinear product in the exact same fashion, where now you're keeping track of, again, it's just like, it's genuine operator product expansions in the usual sense, but not just Q-closed things and their descendants. That's the real take home. Don't just do Q-closed things, you should also consider their descendants. One thing I wanted to point out is that because this coefficient omega n is a 1 form, it's in cohomological degree 1, this operator product expansion has operators of a different parity than what you might expect. Namely, these brackets O1, O2, the nth order bracket has fermionic parity. Or if you have a Z grading, then it's also got a Z grading by the same formula, O1 plus O2 plus 1. Sorry, minus 1. In particular, if O1 and O2 are bosons, this operator is going to be a fermion. And so, aside from that little caveat, everything that you know in 2D holomorphic field theory sort of ports without too many problems into this ravioli setting. So just as an example, everyone's favorite thing in 2 dimensions is a stress tensor. And there's an analog of the stress tensor in these holomorphic topological things. The operator product expansion takes the following form. Turns out that this higher stress tensor is actually a fermion, and its operator product with itself, one placed at 0 and the other one at ZT. It has the analog of a 4th order pole, which is omega 3, something like the central charge. There's a 2nd order pole, which has omega 1. And then there's a 1st order pole, which is omega 0. Plus the normal ordered product, which is what you think it is. Like this. So this is literally just copy and pasting the formula from Wikipedia, but you replace these negative powers of Z with this higher kernel we've been talking about. One thing that should be screaming at you, or maybe I'll scream it at you, is that this thing is a fermion. This guy's got fermionic parity, this guy's got fermionic parity, this guy's got fermionic parity, so this thing better be a fermion for anything to make sense. So these ravioli worlds, this raviolo stress tensor has a central charge with cohomological degree. It's not a number, it's a degree 1 operator. For what it's worth, I don't have any examples with non-zero central charge. I would love to have one. If you can come up with one, I'd love to hear it. There's another analog for current algebras with levels. The formulas are just the expected copy-paste. So rather than give you a whole load of examples, I want to focus on a particular type of example relevant to quantum field theories with extra supersymmetry. So now I want to turn my attention to the holomorphic topological twist of symmetries of holomorphic topological twisted and greater than or equal to 2 theories. So this holomorphic topological twist that we were talking about before is available for 3D theories with n greater than or equal to 2 supersymmetry. N equals 4 is going to be the thing I want to talk about the most. Let's start with n equals 2. The statement is that the HT twist has enhanced symmetries relative to the untwisted theory. For example, if my theory had a G flavor symmetry, this G flavor symmetry gets extended to a holomorphic version of the G flavor symmetry. This is going to be the current algebra version, or the raviolo current algebra version of this G flavor symmetry. And in the same way, it's not just flavor symmetries that get enhanced, but also space-time and supersymmetries. And that's going to be where all the juicy bits are. So what's the expectation? Well, if you didn't know about this symmetry enhancement, you would expect the following. If you start with a superconformal field theory in 3 dimensions, it's got a symmetry algebra OSP n/4, where this n is the number of supersymmetries that your theory has. It's the same n that I had up there. So before twisting, you have this superconformal symmetry, and after, you're going to have something a little bit smaller. You're going to have what I'll call the twist, very cleverly named, of this superconformal algebra. Maybe I'll just call it Q as we did before. And what I mean by this is the cohomology of OSP n/4 with respect to this supercharge Q that we're twisting with. Not all OSP n/4 symmetries are going to commute with Q. The ones that commute will be Q closed. Some of those are trivialized, and so we really have the cohomology of OSP n/4 with respect to our twisting supercharge. And so naively, we would expect a symmetry given by this cohomology, which you can compute to be OSP n-2/2. So naively, you would just expect this OSP2/2 symmetry to be a symmetry of your HT twisted theory. But in the same way that flavor symmetries get this holomorphic extension, this OSP n-2/2 symmetry also gets enhanced.
Sorry, naive question. So, what do you mean by this simplification?
This Lie algebra, I've got a distinguished nilpotent element Q, and I'm taking the cohomology with respect to the adjoint action of Q on OSP n/4. So instead, we find raviolo analogs of superconformal algebras. Two-dimensional ones. As we remember, the conformal group in 2 dimensions gets enhanced to the entire Virasoro algebra. In the same way, superconformal symmetries in 2 dimensions get enhanced to superconformal algebras with infinite number of generators, essentially coming from acting with the Virasoro algebra on your usual supersymmetries. And so just as some examples, of what this symmetry enhancement looks like, if you looked at n equals 2 supersymmetry, so this OSP O/2 is just going to be SP2 or SL2. What we find is this raviolo vertex algebra, Virasoro algebra, sorry. So we find for any 3D n equals 2 theory with an R symmetry, a symmetry by this raviolo Virasoro algebra that I have written up here. And the one I really want to focus on is what happens for n equals 4. And surprise, surprise, what we're going to find is a 2D n equals 2 superconformal algebra, or the raviolo analog. So the last thing I wanted to tell you about is a way to abuse this analogy with 2D superconformal algebras to extract from a raviolo vertex algebra with this n equals 2 superconformal symmetry the Higgs and Coulomb branches of the corresponding 3D n equals 4 theory.
Can I ask some specific questions?
Of course.
This very weak in this super algebra. So say super conformal, 2D super conformal algebra with some like some L subscript n, which are the conformal part, the superscript.
Yeah.
You say the raviolo analog of those algebra, what are the corresponding characters?
That's a great question. Let me write out what that is. So we have this Virasoro algebra.
Actually, I want to explain what is a gamma?
So gamma is the raviolo analog of the stress tensor. So this formula should be compared to T of z, T of 0, C over 2, z minus w to the 4th, plus all the extra terms. And if you wanted to get commutators of the L0, or sorry, the LNs with LM, you would do a certain residue integral of this expression here. And the same way, you can do these raviolo residue integrals on this operator product expansion to get the brackets of the modes of gamma with itself.
So when I get modes of gamma, do I expand in terms of the positive power, the negative power, or do I expand in some different bases?
You're going to use these omegas and z's. So in this expression here, omega zt has a mode expansion n greater than or equal to 0, z to the minus n minus 1, sorry, z to the n, maybe I'll call it gamma n plus omega n gn. This is just like the mode expansion of my field where my modes are now these holomorphic topological. Yeah, exactly. And so given this operator product expansion and this mode expansion, you can start computing the commutators of these modes. So for example, gn, gm is the expected n minus m, gn plus m minus 1. So this is sort of like the positive part of the Virasoro algebra. And then the other modes are sort of the creation operators.
So because you have these like generators, you say your theory has this symmetry because it's generating.
Yeah, exactly. So these gammas are going to be like currents generating the symmetries, which are these contour integrals that I've been talking about. or the symmetry operators are these contour integrals.
But is n equals 4, it takes something more.
Yeah, so for n equals 4, you'll have this Virasoro type field. And in addition to this Virasoro field, you have the analog of a current algebra. I'm going to call the sort of current sigma. It's also a fermion. And its operator product expansion, I'm going to use the usual notation where I drop the regular terms and only keep the singular ones. There's a second order pole, which corresponds to omega 1. And I think it's c over 3. Don't quote me on that coefficient. But the point is the level, quote unquote, of this current algebra is tied with the central charge, quote unquote, of the Virasoro field, which is still fermionic, yeah. Again, the negative modes that we have here, these g's, the ones proportional to gamma, are going to be bosonic for gamma being fermionic. So these guys are fermions, these guys are bosons. In the same way, the modes of these guys proportional to omega are going to be the bosons. They'll generate a GL1Z symmetry that I was talking about up here. And then there's also the creation modes coming from Z. And in addition to these stress tensor and current, we're going to have additional operators, Q plus minus, that have OPEs that are essentially copy and pastes of the superconformal algebra's OPEs. If you really want to twist my arm, I can write them down. They're on Wikipedia, for example. But the punchline is the formulas that you saw in, for example, Wikipedia or your favorite text on superconformal algebras can be copy and pasted without much issue into this raviolo version of the story, where you replace first order poles by omega 0, second order poles by omega 1, and so on all the way up. Of course. And so that's what I mean by the raviolo analog. Each one of those superconformal algebras, for example, just Virasoro, or n equals 2 superconformal, or large n equals 4 superconformal, all your favorite superconformal algebras should have raviolo analogs in this same fashion, where the positive modes agree, namely these ones proportional to omega n. That will be the exact same as the usual superconformal algebra. Exactly. Yeah, exactly. And it comes from this identification here. Here we had a degree 1 thing, whereas in the 2D holomorphic setting, it was degree 0. So all of the modes that were proportional to these negative powers of z now have some shift in cohomological degree. Okay, so the raviolo analog of the n equals 2 superconformal algebra has fermionic generators, this gamma, which corresponds to a Virasoro field. We have a fermionic generator, sigma, which corresponds to like the superconformal current. And then we have two bosonic operators, Q plus and minus, that correspond to the supercharges in the n equals 4 superconformal algebra. Sorry, n equals 2 superconformal algebra. So this story I want to tell you about is how we can repeat a story in two-dimensional superconformal algebras to extract Higgs and Coulomb branches from the raviolo vertex algebra coming from the holomorphic topological twist of an n equals 4 theory. And the thing we're going to do is compute the chiral ring, or the raviolo analog of the chiral ring. So let me remind you about chiral rings. This is something I mentioned a little bit in the pre-talk. The basic statement is the following. we consider a certain type of operator called a chiral operator. So we have an operator O, and we call it chiral if it's operator product with the supercharge G plus, which will be Q plus in our ravioli story. It has a regular OPE with G plus, and its operator product with G minus is not regular, but has a first order pole where there's an operator I'll call lambda sub O with a first order pole, no second order pole or higher. Such an operator O is called chiral. And then the fun fact is that given chiral operators, their operator product expansion is necessarily regular. And this follows from a BPS bound. So I guess I'm talking about unitary theories. Yeah, exactly. The usual notation in n equals 2 superconformal field theory calls these guys G. It's sort of an unfortunate notation because I called this thing G. But this is these will be the analogs of Q plus and Q minus. Superconformal currents. Superconformal charges maybe. So because these chiral operators have regular operator product expansions with one another, we get a commutative associative product on chiral operators on the vector space of chiral operators, where I define O1, O2 to just be the normal ordered product at the same point. So seems like silly notation, but it's just the normal ordered product of O1 and O2 evaluated at that point Z. And this is commutative and associative because of this regularity of the operator product expansion. In general, normal ordered products are very far from commutative or associative, but if the operators have regular operator product expansions, then the resulting normal ordered product is in fact commutative and associative. And of course, we know that we can do yet better. If we look at operator product expansions with these descendants that we were talking about that show up in this OPE with G minus, they encode a Gersten-Haber structure. Also called shifted Poisson, one shifted. And very roughly speaking, this bracket is as follows. It's equal to dx over 2 pi I x minus w psi O1 psi O of z, O2 of z, plus or minus psi O2 x O1 of z. And so you can show that this defines a derivation of this product. It's also graded symmetric in a shifted sense, i.e. it's a one shifted Poisson bracket. If you're familiar with topological strings or topologically twisted quantum field theory. This is the Gerstenhaber algebra structure on Hochschild cohomology of your category of branes. Or said differently, it's the cohomology of an E2 algebra. You can play the exact same game. And an n equals 2 superconformal raviolo vertex algebra. And again, let me remind you that this thing is the structure that one has from the HT twist of a 3D n equals 4 theory. We end up getting a similar setup. This constraint can be applied there. We can ask for a regular OPE with the operator Q plus and a first order pole with the operator Q minus, and define those local operators to be chiral. I'm going to call them Higgs branch chiral operators. They satisfy this constraint where the OPE, this sort of higher OPE that we've been talking about with Q plus is 0, and the higher OPE with Q minus has a first order pole, i.e. omega 0, with an operator I call psi O. And then playing the same sort of games, you find that for two chiral operators, their higher OPE is necessarily non-singular. And you can define a commutative associative product via this normal ordered product we've been using. And in the same way, we can actually define a shifted Poisson structure by doing an analogous contour integral using this superpartner psi 0. But as we saw before, the bracket is also sort of already a shifted bracket in some sense. These omega n's that we've been talking about before have degree of their own. And so what we end up finding is that we get a two-shifted Poisson algebra. Yeah. Yeah. Yeah, that's right. Yeah, it's a holomorphic. It's a propagator where your kinetic term uses this d prime rather than like del bar or something. Yeah, yeah. So it solves the one for a Green's function. So if you look at this thing I was calling del bar plus this is sort of like the kinetic operator applied to omega 0. This is equal to, maybe throw on a dz in there. This is a delta function at 0. Or sorry, delta function z. So it's a Green's function, where the differential operator I use is this holomorphic-topological de Rham-Dolbeau operator. Omega 0 is a 1 form, yeah. This is 1, this is 2, this is 3, equals 3. Okay, so surprise, surprise, the bracket we get is again a shifted Poisson bracket. But now it's two shifted because our Our omega 0 terms are shifted in cohomological degree by 1. So we get a 2-shifted Poisson bracket. So at the end, we find that the Higgs branch chiral ring is a 2-shifted Poisson algebra. You should think of this as perhaps the cohomology of an E3 algebra. Of course, we haven't done a cohomological thing here. We've just mirrored the construction in 2 dimensions, where we get a sort of topological subalgebra out of our holomorphic thing. Here we get a topological subalgebra of our holomorphic topological thing. There's another type of ring that you can get called the twisted chiral ring, where you replace chiral by twisted chiral, and you flip G plus and G minus. And surprise, surprise, there's another chiral ring in 3-dimensional n equals 4 quantum field theory, the Coulomb branch chiral ring, and it arises by doing the twisted chiral ring construction. We do this in a family of examples in our paper from last Friday. They all match, which is great. Unfortunately, we can only do free theories for the moment. I would love to be able to describe interacting theories, and that's just a matter of some more work. So with that, I will say my last little blurbs. I've taken more than enough time. Yeah, at the very least, Z2. So this is like 2 mod 2 if you work Z2. This superconformal current that is over here gives the grading that makes it a Z grading. So it is Z graded, so long as you started out with something that was Z graded. Yeah. You just forget that it was 2-shifted and just remember that it's even. So it's a genuine Poisson bracket. And if you remember the Z grading that scales the symplectic form with weight 2, then you get the 2-shifted Poisson bracket. So the last few things I wanted to mention. The first one is that this raviolo that we've been talking about is not formal. What this means is that I have this DG algebra of functions whose cohomology is this thing generated by Z and omega. It is not equivalent to the cohomology, it's not equivalent as a DG or A infinity algebra to the full chain level functions on this raviolo. So the sort of take-home message is that there are yet higher L infinity or A infinity type operations that haven't been talked about.
Do you know what it would mean?
I would love to know. The thing I can say is that based on computations in these holomorphic topological quantum field theories, what you end up finding is things like, if I look at correlation functions of local operators in a line, I get some sort of A infinity-like thing that sort of depends on how these points are ordered on the line. Other than some little baby examples, I haven't seen a whole lot of structure. Some people, there is a notion of associativity for raviolo vertex algebras, which is analogous to the notion of associativity in chiral algebras.
You don't think
That one probably won't fail. That one might be the thing that gets weakened, actually. This associativity in the usual vertex algebra setting is some statement about a Jacobi identity of commutators of your modes, and the failure of the Jacobi identity is what leads you to L infinity things. And so that's a very good point. That's probably the thing that gets weakened. This associativity notion is probably the thing that gets weakened. Some people call or hope to call it the resulting thing an what is it? It's a E1 chiral. Insofar as that thing's not defined, I can't tell you whether it's the right thing or not. But people call whatever it's going to be E1 chiral.
So E1 is the R direction?
E1 is the R direction and chiral is the C direction. So this is what they call what this thing wants to be. And we have a chain level version of the mode expansion, but we weren't able to come up with a chain level version of the associativity axiom. And that's the thing that you would really need to be able to access these L infinity things. I mean, we have vague ideas of what we should be aiming for. The question is, how do we come up with a nice model for functions on these higher configuration spaces? So the L infinity operations, L2 is just the bracket, which comes from these configuration spaces of 2 points. And the higher arity brackets come by looking at higher arity configuration spaces. And we just don't have a good model for functions or derived model of functions for those spaces. We have it for the configuration space of 2 points, but to formulate things like locality of operators and associativity, you need the 3-point spaces.
The points in the C cutoff.
Yeah, exactly. Yeah. Spoken about. So what we need, a good model. The configuration space of endpoints on C times R, this sheaf of HT functions. We have one for N. Maybe I will put chains rather than cohomology, because chains are where you should be working. We can do N equals 2. We present a DG model for functions for N equals 2 in our paper from August, but the higher arity configuration spaces don't yet have a good description. No, locality is fine for N equals 2. The hard part is when you try to formulate associativity.
Right.
And that's where the L infinity thing sits for the usual chiral algebras. And it should be where the sort of L infinity parts of this shifted Poisson thing are.
And locality is like map on the nose, or it's like homotopy?
I mean, insofar as I don't know what a homotopy vertex algebra is, I don't exactly know what the right replacement is.
No, I meant like in the raviolo vertex algebra, the statement of like locality is just map on the nose.
Yeah. So in the raviolo vertex algebra story, exactly as you say, associativity is essentially like a translation of Frankel-Benz-V. But you just use this different ring. You don't use C adjoin Z and Z inverse, you use this sort of DG thing. If we had an analog of the space, like in the formulation of associativity, you have like the space CZW, Taylor series, Z inverse, W inverse, Z minus W inverse. Like this is the sort of ring of functions that you look at when you're talking about associativity, and everything is fine in 2 dimensions because it's all affine. But we don't have a good model for what this space should be in this setting of ravioli things. And so some questions that I'll leave you with trying to aim for. The first thing is that most of these things are totally like open territory. This is like a brand new thing that if you think sounds cool and you like vertex algebras, this is a fun place to play around. So here's some questions that I'd love to have answered. I would love to have examples of these raviolo vertex algebras coming from physics, not just the sort of abstract nonsense I've been telling you about, with non-zero central charges. Yeah, so I had this operator product expansion for the raviolo analog of the Virasoro field. There's a 4th order pole, so omega 3, where I had this operator C that has interesting cohomological degree. It is not a number, no. It's an operator. 2 gamma plus omega 0 del gamma. So I want examples where this thing is not 0. It doesn't seem like it's going to be quite so simple because we're taught back in quantum field theory that there are no anomalies for local symmetries in odd dimensions. And well, this is a symmetry in odd dimensions, so it's not clear how to get the same sort of appearance of central charge that you do in 2 dimensions. It's likely to have some relative structure where you have some 4-dimensional theory with a 3-dimensional theory on its boundary, and this is realized via inflow or some analog of that. I can sort of sketch ways of getting levels for current algebras in that fashion, but I'd really love to see a central charge showing up. Another question that I'd love to be able to understand is, what's the raviolo analog of conformal blocks? In 2-dimensional vertex algebras, we have conformal blocks that control correlation functions on Riemann surfaces. In this raviolo land, we wouldn't be talking about Riemann surfaces or the moduli of Riemann surfaces. We would instead be talking about the moduli of transverse holomorphic foliation structures on topological 3 manifolds. Yeah, so it definitely includes the usual moduli space where you do exactly as you suggest. But there's much more interesting types of THF things than just these split ones. And so there should be some statement about how you can look at correlation functions on one of these THF manifolds and ask, how do my correlation functions vary in the moduli, and whether there's some sort of version of conformal blocks and what does it correspond to. There's this sort of VOA topological quantum field theory story where conformal blocks are related to state spaces in a higher dimensional theory. And I might imagine a similar story happens here where you have a three-dimensional holomorphic topological theory on the boundary of a four-dimensional theory, and the analog of these conformal blocks are some avatar of the space of states of the four-dimensional theory on time times that Riemann surface. Sorry, THF three manifold. Three more things. I'll just mention two of them. I was mentioning in the pre-talk that there's actually a relation between these raviolo vertex algebras and genuine vertex algebras. Well, they're a model for the cohomology of the derived center vertex algebra in the usual sense. And this is directly analogous to the usual statement about Hochschild cohomology. If we have some two-dimensional boundary of a three-dimensional space that supports a vertex algebra, V del, then the raviolo vertex algebra in the bulk acts on this boundary in a couple of ways, in fact, infinitely many ways. The first thing you can do is just bring a bulk local operator to the boundary. That's one type of action, and that's the usual center action. Everything that comes from the bulk has to be central in the boundary. But there's also higher operations, where if you had some boundary local operator, you could imagine trying to integrate a bulk local operator along a hemisphere surrounding it, or some power of z to the n or omega to the n. And in this fashion, raviolo vertex algebras should in some sense act on genuine vertex algebras in that they are sort of the symmetries of vertex algebras as well. There is some precise mathematics that goes behind this one, so it doesn't seem like such a far-fetched thing. Temerkin, in the world of chiral algebras, is able to show that there's a chiral algebraic analog of raviolo vertex algebras that is the genuine derived center of a chiral algebra. And so translating that to vertex algebras should be some statement about how raviolo vertex algebras are, well, derived centers or Hochschild cohomology of vertex algebras. That's so chiral algebras and vertex algebras are, I don't know if they're entirely equivalent, but they are meant to be just two different ways of describing local operators in a holomorphic quantum field theory in two dimensions. A chiral algebra, rather than being some statement about algebras of local operators acting on themselves, are related to certain D modules on a thing called the Ron space of a complex manifold X. Morally speaking, this is like the configuration space of points on X in all orders together with their various gluing properties with one another. And rather than talking about like an algebraic version of the 2D holomorphic quantum field theory where you have these modes acting on a vector space, this is a geometric incarnation of that same thing in terms of D modules on a specific space X that depends on your spacetime. X is a Riemann surface in the sort of Babius setting, but you can consider more general algebraic varieties in any dimension. So these are like strictly more general than vertex algebras, and they overlap in most of the examples you could ever think about, but the translation isn't, I mean, in the examples that are well behaved, it's a pretty easy translation, but I don't know if it's exactly one-to-one. Because you can use geometry here rather than algebra, you can really push it a lot further. And so these guys are quite powerful, but they are much less explicit. And then the last thing I want to mention is that this story of turning these configuration spaces of points on holomorphic topological spaces gives us lots of footholds in generalizing vertex algebras to a higher dimensional setting. So rather than talking about holomorphic quantum field theories in 2 dimensions, you can ask about holomorphic quantum field theories in 2n dimensions. And the algebra of local operators should be some generalization of a general vertex operator algebra. And the statements about operator products being non-singular happens as well because of the actual Hartog's lemma. But there is higher cohomology. And the same way we treated the higher cohomology here, one should be able to play similar games in higher dimensions to get higher dimensional analogs of vertex algebras. The last thing I'll mention, if you're at all interested, there's some cool things that can be said about M2 brains. If you take M2s, they're 3-dimensional world volumes, you can twist 2-dimensional, or this M2s to get a HT twisted 3D n equals 8 quantum field theory. There's an analog of these raviolo vertex algebras for those theories. I'd love to know what they are. We have a notion of what the symmetry algebra is that governs them, the analog of this n equals 2 superconformal algebra I've been on about. And it would be really great to be able to understand some structural properties that you can learn about M-branes from that symmetry algebra, or at least twisted world volume theories. Okay, well, I've taken more than enough time. Thank you so much for your patience and for inviting me. Do you have any questions? I haven't tried, but I would imagine if you looked at these vortex moduli spaces on the raviolo, they should have the structure of one of these raviolo vertex algebras.